Well, it's a pleasure to be back at the Newton Institute, and I'd like to thank the organisers and agreeing to pay my travel costs. What I'm going to talk about today is an outgrowth of something that happened about 18 months ago. I need to switch this on, don't I? Yeah. How's that? Yep, we're there. So, about 18 months ago, there was a meeting or start of a meeting at SAMSI in North Carolina, and this was organised by Simon Godsell and Arnaud Doucet. And part of that was a spin-off activity, a working group on continuous time methods, which I partook in, and also Paul Fernhead and Jochen Voss were members of that group, along with others. And the idea was to try and understand how we could use particle filtering ideas in the context of continuous time models, of diffusion type models. And the reason I was drawn to this area of activity was because it seemed to me that there was somehow more scope for innovation in that area than in classical discrete time particle filtering stories, where we have in our minds this universal paradigm for how a particle filtering algorithm will go, and there's of course a lot of ingenuity required to make these methods work well in any particular application, but the template is always the same. Whereas in continuous time you have this idea that there's perhaps sort of methods of calculus that you might be able to draw on that might allow you to approach some of these problems in a different way. And that's indeed what this work is about. So what I'm going to talk about is I'm going to just say a few things about what I mean by least action filtering, which is not going to introduce ideas I think that are particularly novel to anybody in this room. And then I'll discuss how we pick out the least action path. So this is a sort of maximum likelihood idea. I mean, it's not really kind of anything Bayesian in the sense. It's sort of maximum likelihood. And then I'll talk about how you then approximate the distribution of the path around the sort of maximum likelihood or least action path. I'll give you, I say examples, it's just going to be one example, this is still in progress, and then I'll just say a few words about what this looks like when we try and think in terms of particle filtering and why these sorts of ideas may be of some benefit in that context. There's a paper by Markussen recently who uses some similar techniques to approximate the density of a discretely sampled diffusion process, though I think the form of the results he gets and the form of the results I get are not always evidently the same. Okay, so let's take a look at the setting. So the idea is that we're going to have some diffusion process in RD, so it's a vector process, Z, and we'll partition it as X and Y. So think of X as being the top piece of the vector, Y is the bottom piece of the vector. And Y is what we're going to observe, and X is what we're going to try and make inference about. And this process Z will obey some possibly time-dependent autonomous stochastic differential equation driven by Brownian motion. And we'll make sort of minimal assumptions. The vol and the drift are C2 bounded with C2 with bounded derivatives, and the inverse likewise. Okay, so that's the basic technical setting. So as I say, we observe the process Y, and we want to know the conditional distribution of the hidden path X between time naught and time capital T. And closely related to this problem is a sort of time discretization of it, the first order Euler scheme, where you just, as it were, fix at each dyadic, take each 2 to the minus n dyadic interval, and at the beginning of that interval you fix the time component, you fix the space component, and you use that constant volatility, constant covariance structure there, and a constant drift throughout the interval of length 2 to the minus n. So in effect it's like a bunch of a sequence of Brownian motion pieces with constant drift and constant covariance. So it's a very, very simple idea, and as you let n go to infinity, this first order Euler scheme will approximate the SDE closely, as you'd expect and hope. And again, despite appearances, you can think of this as a discrete time story if you simply look at the times multiples of 2 to the minus n. So here we are now, we know where we are now, we know what vol and drift we should use, so that tells us the distribution of where we're going to be after a further 2 to the minus n of time has passed. We've moved on average through
mu times 2 to the minus n, and we've got a covariance sigma transposed times 2 to the minus n. Okay, so that's all it is. You can just piece it together in a very, very simple-minded way, each discrete time step by discrete time step. And as I remarked, that you have a convergence result, that these first-order Euler schemes will converge to the solution of the SDE. So looking at the SDE or looking at the first-order Euler scheme is more or less the same thing. Okay, so that's the sort of first point I want to make, that we don't have to, we don't have to feel that we've got to do analysis in continuous time. We don't have to feel that we can only do analysis in discrete time. Somehow these two things are close, and I want to exploit that closeness and use elements of continuous time when they're convenient, and use elements of discrete time when they're convenient. Okay, so we are relaxed about this. So it's very much the spirit that Pierre was describing, 45 minutes ago, that we can write down equations in continuous time, but we need sometimes to think in discrete time to see things simply. And indeed, my attitude is that we will use continuous time for guidance, and we'll use discrete time for numerics and proof. Okay, if we're going to calculate something, it's got to be made discrete. So why do we bleed over continuous time stories? What's the point? Okay. All right, so let's look at some log likelihoods and follow this through, because as I say, all I'm doing is very, very classical stuff. It's maximum likelihood. Okay, so let's think in our discrete time story for the moment. We're seeing a sequence of observations which are coming from this discrete time dynamic, and we want to estimate, or we want to find the conditional law of the bits of the process that we didn't see, the x's. Okay, so I'm using lowercase to denote discrete time versions of the uppercase, which are continuous time. Okay, so what's the log likelihood look like? Well, let's go into here and take a peek. So what we've got is we've got a sequence of Gaussian transitions. Okay, they're conditionally Gaussian transitions. So if we look at the transition from time jh to time jh plus h, where h is just this little time step 2 to the minus n, well, it's got a mean h times the drift, or the drift as it would have been at the beginning of the time interval, and the covariance is sigma transpose times h. So this term, the jth term in this sum, is exactly the log likelihood of the step from time j to time j plus 1. Okay, and then we have the log of the prior here, minus 5x naught. Okay, now if we simply divide through here, take a factor of h out of the expression inside the modulus, that combines with the 1 over h outside to give us a factor of h, and then we've got a squared modulus of something that's been renormalized. And if we look at what this is a sort of Riemann sum approximation, if you wish, to the integral of the modulus of sigma to the minus 1 z dot, the time derivative of s, minus mu. Okay, so it's a very, very simple idea. This is the difference quotient here for z. Think of z as being some path that actually has a continuous time trajectory. We're looking at the difference quotient. This is an approximation to its time derivative, and that approximation taken at time jh. Okay, so this is, this is somewhat formal, because to begin with, this process z was only defined discretely. But remember, we're relaxed about discrete and continuous. Okay? Yeah, I'm not saying this is equal to. I'm saying this is equal to. Okay, now in speech it's the same, but in writing it's very, very different. Now, okay, look, I mean, let's not get tied up on these difficult things, because, as I say, we look here for guidance, we look in discrete time for proof. Okay, so this is the thing then. So if we're going to try to maximize the log likelihood here, this is the true log likelihood, which we see is approximately this thing. Let's think about how we would maximize this. Now, what we're seeing here is a process z, or a path z, which we now imagine has been evolving in continuous time. The bottom part of it, the y part of it, is something that we saw. The x part of it, the top part, we didn't see, and we're trying to understand what the x was doing. Okay, so we're going to look at this integral functional, the action functional here, and I'm going to abbreviate this this squared modulus here to the functional psi. So it's psi of time and x and p, where p is the time derivative of x. And we don't need to include the value ys and the value y dot s in this notation because we observed those, and those are, for current purposes, deterministic trajectories. So those are absorbed into the time dependence here, and the only thing that matters is the x and the p. Okay, because those are the variables that we're going to try and maximize over. Okay, so we're going to take this functional and we're going to try to optimize it. And, well, this is what we would teach our students. This is a problem of calculus of variations. So let's see where that takes us. And if we look at this, we're going to do a perturbation of a presumed optimal x star to an x star plus psi. So we make a little perturbation away from the optimum. We see what the change in the objective is to first order, and we equate that to 0 because if it's not 0, we weren't at the optimum. So we look at the little change in the log likelihood, and remember the log likelihood is written out as this integral together with a term from the prior distribution. We make a little change, and when we make the little change in x, we get a derivative of psi with respect to x times the change in x. And when we perturb x, we've perturbed x to the derivative of x to the derivative of x star plus the derivative of psi. Okay, so we get just these two terms. That's all that comes from the first order change in that. Okay, so that's all we have to see. And then the change in this is just, again, calculus. You change the point x naught, you get the change in x naught times the gradient. Okay, so that's all there is. And now, as you would always do with calculus of variations, you have a time derivative of psi here, but psi there. What do you want to do? You want to take that time derivative and put it onto the dp by dp of psi. You want to shift it, integrate it by parts. So let's integrate it by parts. So we'll get an evaluation of psi times the gradient of psi with respect to p out front, and then included in the integral, this was the term, the psi dx d psi term carried down, but now we have just a time derivative of this dp of psi along the path that we observed. So you get the three terms which correspond to the derivative of psi with respect to time, with respect to x, and with respect to p. Okay, so this is just, second year undergraduate calculus. Nothing complicated. Okay, now the story of calculus of variation says that psi should be allowed to be arbitrary, and since psi is allowed to be arbitrary, that all of the things that get multiplied by psi have to be 0. So we've got terms involving, terms along the path here in this curly bracket. We've got terms at time 0 here and in here, and we've got terms at time capital T in here. So if we simply pull those terms out, the time 0 term, here's the dx of phi. Here is the contribution from the lower limit of this evaluation. Along the path, we have this equation, and at time capital T, we have this. So altogether, what we've ended up with is a second order ODE for the optimal path x star with boundary conditions at 0 and at t. Okay, so this is the maximum likelihood path, the least action path, and given the observations y, this is, as it were, our best guess at what x did. Okay, so let's just briefly look at how this would carry through if we were to actually try and do this properly and tell the story in discrete time. So if we try and tell the story in discrete time, we write down the same thing. We have a sum instead of an integral, so we have a sum of the step times the value of psi on that step. And now we do a calculus of variations, and we perturb, just as we did before. We get a change due to the change in x. So this is the change in x times the gradient. And then we get the change in p, which is the difference quotient of psi, times the gradient of psi with respect to p. Okay, so that's all that happens. It's just the same. And previously we integrated by parts, now we sum by parts. And we rearrange this sum. This xij plus 1 goes in with this to give us a term here. And we get a sort of difference quotient of d psi by dp, and we get various terms at the start and finish. So when we look at this expression, everything that gets multiplied by this arbitrary psi has got to vanish. So this gradient has got to vanish, this expression in the curly brackets has got to vanish, and this expression in the curly brackets here has to vanish all the way along the path. So if we think how we would try and to solve this, if you start off with a particular value of x naught and you say this bracket here has got to vanish, well, p naught is going to be x1 minus x naught, so that gives you a system of equations for p naught, nonlinear equations for x1. So you solve these and you deduce x1, and then you go into the first term of this and you look at the first term of this, and everything in the first term is known except for p1, which involves x2. Okay, so you've now got a nonlinear equation to solve for x2, and now you go through the terms one by one and gradually work out what x3, x4, and so on will be. And when we get to the end, we've got xn minus 1, and we have to have that the final term is also going to vanish, and that's a sort of condition that's got to be matched up. So it's very much like the sort of shooting problem that we had in the ODE, and what we're looking at is an implicit discrete scheme for the ODE. Okay, so it is the ODE but just discretized. Okay, so this is rigorous, and what we were doing on the previous slide was not rigorous, but it was much more comprehensible. Right? Okay, so that's sort of what we're doing now. Let's now look at the second order story, because what we're doing is very much like we were doing classical statistics. We form a maximum likelihood estimator, but in order to use use some sort of statistical test, you use asymptotic maximum likelihood theory. You say, well, the likelihood surface is maximized at this point, but near the maximum it looks like a quadratic. So we have sort of tests based on asymptotic normality for estimators. And now let's see what the analog is in this context. Okay, so we've got to consider expanding the action functional not just to first order, which will give us the maximum likelihood path, but then go to second order and see what that tells us. Okay, so if we expand to second order, all of the first order terms in the expansion disappear, because that's by definition we were at the maximum, so the first order terms have gone. So all that remains is the second order terms, which are quadratic in the perturbation psi. So we have a little bit to do with what happened at time naught, and then we have a whole load of stuff along the path here. So we have the second order terms in the Taylor expansion of psi around the optimal point. Okay, so we're getting terms involving psi squared, psi times psi dot, and psi dot squared. Okay, so we're getting quadratics like that. And just for brevity, I'm going to abbreviate dxx psi to at and correspondingly bt and qt. And it's important to recognize that these things are actually just now deterministic functions of time. They're deterministic matrix-valued functions of time. They're the various derivatives of the functional psi evaluated along the maximum likelihood path. Okay. So these are things which in principle we now know, and the question is, what does this likelihood look like? It's quadratic in the perturbation psi, so it's telling us that whatever the perturbation is, it's going to look Gaussian. Right? The log likelihood is quadratic in the perturbation, so the perturbation is going to be a Gaussian process of some kind. And the goal now is to try and identify as clearly as we can what that Gaussian process actually is. Okay, well let's see. Now, if, and this is a big if what's inside the curly brackets in here is actually a perfect square, so in other words, we can write it out as psi dot plus k times psi in a product with q times psi dot plus k times psi. If that were true, then certain things will follow. But in general, it's not going to be true, because the right-hand side implies certain relations between the matrices A, B, and Q, which do not necessarily have to hold in general. Okay? But if it is, then we can be very much more explicit about what the quadratic we're looking at actually is, what the Gaussian structure of psi will be. Okay, well let's look. If we have this, let's set w dot is root q times psi dot plus k times psi, and if we do that, what's in here, equivalently this thing, is just w dot squared. So the functional q that we're looking at is this. So we've got a little bit that involves what's happening at time naught. Well, this is clear. This is just the log of a Gaussian density. And then this bit, what's this? This is the action functional for a Wiener process. Okay, so what it's telling us then is that we should expect that psi naught will have a normal with zero mean and this covariance, and when W is a Brownian motion, the perturbation psi should solve this first order linear stochastic differential equation. Okay, so that's the whole structure, if we have that particular property relating the three matrices A, B, and C. So this is easy to grasp, isn't it? I mean, we've got a linear equation. I mean, this could be, you know, like minus a constant. It would be an OU process. Okay, it's clearly Gaussian. It's clearly zero mean, and we can even calculate the covariance of it, which is a matrix which solves the first order differential equation. So there's no mystery whatsoever about this process psi. It's as concrete as it possibly could be, provided we've identified the K and provided we have the condition on the three matrices A, B, and C, which, as I've said, in general, we don't have. Okay. However, we can make it happen. And here's how. Give yourself a symmetric matrix valued function theta, which vanishes at time capital T. Okay? Now, let's look at this. This is the quadratic functional that we care about. Okay, and the thing we care most about is this bit in the middle, this integral term here. Now I'm going to add on in red, which on my screen was extremely visible and now is almost indistinguishable from all the rest of it. I'm going to add on some terms in red. Okay, so I'm going to add on an evaluation of psi dot theta psi between 0 and t. And I'm going to do something else over here, which is in red, and nothing has changed because when we're at t, theta t is 0 by construction or by hypothesis. Theta t is 0 by hypothesis. So there's no contribution here, and at 0, the contribution that we will get has been absorbed in here. Right? So nothing's changed. Line 1 equals line 2 trivially. Now what then happens? Let's take this evaluation between the limits, and let's just write that out as an integral of the derivative between the limits. So if we differentiate this thing, we're going to get a half psi theta dot psi, which is differentiating theta, and then we differentiate the psi or the before or after, and we'll get a psi dot theta psi. Okay, so that's all that happens. So the blue bits are exactly what they were before, and we've got these two additional terms added into the integrand. Okay, that's all that's happened. Now, if we look at this business inside the curly brackets here, this business here, we combine everything involving psi dot squared, which is just q, psi dot is b plus theta, psi is a plus theta dot here. Now that will have the exact square form, provided certain relationships between this matrix and this matrix are satisfied. That will actually hold true provided, if you look at the cross terms, q times k is b transpose plus theta, and if you look at the final term in psi squared, a plus theta dot is k transpose qk, which of course is b plus theta, q to the minus 1 b transpose plus theta, if the first thing holds. So what we're seeing here is a condition relating theta dot and theta involving known matrix functions of time q, b, and a. Okay? So in other words, we have a differential equation for theta. So provided we can solve that differential equation, which we can, it's just a first order differential equation, along with the boundary condition theta t equals 0, which we can, of course, then we found a theta which converts the quadratic form into a perfect square. And then when it's converted into the perfect square, we understand how the perturbation x minus x star behaves. It's a Gaussian process. It's a Gaussian process with a covariance q to the minus a half and with a drift term kt times psi. Okay, that's it. So this gives us this simple probabilistic picture for the trajectory of x conditional on what we saw. We work out the least action path by solving a second order ODE with boundary conditions at time naught and time capital T. having done that, we work out the sort of the magic theta, and we then deduce what the psi will be, where psi solves this linear equation. Excuse me. So it's as pretty as it could be. You've got the maximum likelihood path, you've got the perturbation around it, which is just a linear Gaussian process. It couldn't be cleaner. Particularly if there are no observations, this gives us a way for approximating the law of the diffusion itself. So we're saying that the diffusion is approximately a maximum likelihood path plus a Gaussian process. The methodology that we're using here relies on solving ODEs, and of course this is a very, very developed technology. I mean, you know, applied mathematicians have spent decades developing the conceptual methods and the numerical methods to solve ODEs in arbitrarily large dimensions, in effect, and very efficiently. So we're tying in the problem to a very, very strong base of existing numerical methods. And so it may stand a chance of working well in high dimensions, and by that I mean sort of dimensions, say, between 10 and 20, which, you know, conventional, say, Monte Carlo methods start to struggle with. So I see this as being a sort of a way of trying to kind of push particle filtering and other such SMC methods into higher dimensions than they would normally be able to handle. Okay. Let's maybe have a few words. Oh, I've got an example. Yeah, this isn't very. It's not a very sexy example. Come on, but you know. Let's suppose you've got a couple of one-dimensional OU processes, independent, let's say, x and little y, and what we see is the process x of interest plus the noise process y. Okay, and we're going to try and, okay, so this is just a Kalman filter, come on, this isn't deep, but at least because it's a Kalman filter, we know what the answer should be, and it's all okay. So now we have a sort of linear dynamic for z, and it partitions, the matrix Z partitions neatly into x and y. We've got everything, and then the functional psi is this nice quadratic of p and x. So everything is available explicitly. And here's a little plot of what happened on a time horizon of 200. We've got the true x is the black sort of dot dashed line there. The observation was y, and the blue is what the least action filter picked out. So it looks kind of right. I mean, you know, I should have gone and done the calculations and worked out what the Kalman filter would have given us, but I bet it's pretty close to the blue. Okay, so it did something sensible, at least on that toy example. Okay, well, let's just have a few words about particle filtering, because you know, this was really where this study began, was trying to think about particle filtering. Volume of a ball in radius of radius 1 in dimension d is this expression. So, you know, you can sit down and spend 5 minutes of gentle enjoyment re-deriving that for yourself, or you can go and look it up on Wikipedia. I don't care, but that's what it is. Now, how does that depend on d? Well, let's sort of look into that. Suppose we've got a ball b of radius little b hidden somewhere in the unit cube in d dimensions, right? So we've got, you know, a cube in d dimensions. We can visualize it in 3, and we can pretend we can visualize it in 4, and after that it's just something kind of beyond our imagination. Okay, but it's a cube. It's got volume 1. And we might think of this ball b as being the ball where the likelihood of a given observation, given the true position x, is bigger than epsilon. So we might think that we've got some sort of hidden value x, we see a y, and we're doing some sort of particle filtering attempt to kind of put particles near to y, right? So when we just sort of fire particles into the cube in the simple-minded particle filtering methodology, we want to get particles that come close to y so that they have high posterior likelihood and they get weight, and the other particles we kind of forget about because they missed the ball. So we're trying to fire particles into the cube and hit the ball. That's what we're trying to do. So the question is, I mean, how many tries do we need? How many times do we have to fire a particle into the cube to stand a reasonable chance of hitting the ball. Okay, and the answer is, well, it's roughly going to be 1 over the volume. Yeah. So you need, on average, about 1 over the volume of the ball in order to hit that, because that is the probability that a randomly chosen point is going to fall into the ball. Because the cube is unit volume, and that is the volume of the ball. So that roughly is the number of particles that we would need to be firing into the ball to stand a chance of firing into the cube to stand a chance of hitting the ball. So this is just the sort of particle filtering 0.0. The simplest thing you could possibly do. And what does it look like? Well, dimension, and this is log to the base 10 of the number of points, right? So just the log to the base 10 of this thing. In dimension 10, it's about, what, say 7 or 8? So we're talking about 10 to 100 million particles to stand a chance of hitting a ball, in this case, a ball of radius 0.1, which is not particularly small. Right? So we're going to need 100 million particles to stand a chance of getting 1 particle in the ball. Okay, and it's clear that the dimension just annihilates the simple-minded particle filtering methodology. I mean, it may be okay down here at 5, but once you get out to 15, there's absolutely no hope. At least not with this crude, simple-minded approach. You simply aren't going to get there. Right? Just firing particles in and hoping won't do it. Okay, so what could you do? Well, I mean, the guys in particle filtering have thought about this, of course, a very long time ago, and you use importance sampling. So you don't just fire the particles into the cube without thinking what you're trying to do. It's quicker to think and then fire fewer particles than to fire lots and lots and lots and lots of particles. So you stop. While the computer's, on the 4th day that it's grinding away and you still haven't hit the ball, you think maybe it's worth spending 20 minutes with pencil and paper before we go any further with this problem. And importance sampling is the trick. So suppose, for example, you had a situation where the y that you were going to that you saw was some true value x plus say a Gaussian error term. Then what you'd try and do is you'd say, well, okay, these x's might be, say, have some distribution, but given that we've seen y, that sort of tilts the distribution it draws the distribution of the conditional distribution of x towards the point y. Okay, so we should be sending our particles towards the point y. Okay, so what we would do is we would maybe use a proposal distribution that was centered at y, and then we'd fire lots of particles in. They'd all get reasonably close to the observation y, but then we would have some sort of down weighting because we'd used a readjusted probability. So we'd have to take that into account, but we would at least stand a decent chance of getting the true value. Here's one. You should do this with your students. This is a lot of fun. W is a Brownian motion. What's the value of that? I was hoping somebody else could tell me. We know. It's 1. Yep. Okay. Now you simulate that. You're trying to achieve that by simulation. Simulate yourself, 10,000 particles with a normal 0t distribution, and take the average of that expression. Now it should be 1. Now it's okay if t is about 1 or about 2, but you push t up to 10, and you'll get an answer about 0.3. Right? And the reason is exactly the problem that we're facing here, is that we generate many particles, but this expectation is 1 precisely because the thing that we're taking the expectation of is very large on a very small probability set. And if we simply generate normal 0, 1 random variables, all of the particles that we've generated miss the place where the integrand is large. And that's exactly, in one dimension, that's exactly the problem that we have with simple-minded particle filtering. So to understand this, of course, we would interpret this as being a Brownian motion with a drift. We would generate particles with the normal distribution but shifted according to the drift, and we would get the answer 1 pretty well perfectly. Okay, so that's what we have to do. But it's not always as simple as that. Suppose we were in a situation, I mean, this is a situation where I've actually been trying to do things where, say, the observation that we get is some very complicated nonlinear function of some hidden variables. So in particular, I was looking at some, trying to calibrate certain models to financial data, so say option prices, and the price of the option as a function of the underlying is a very complicated nonlinear beast. And we might be trying to, say, fit prices of 20 derivatives, so y is 20 dimensional, let's say, and we've now got to try and draw the particle x towards y because we're in high dimension. We've got to do importance sampling. Well, how are we going to do the importance sampling? How do we know what values of x are close to give us values phi of x that are close to y? It's a maximum likelihood. We're doing maximum likelihood. We have to find, we have to search over values of x to minimize the distance between y and phi of x, or something of that nature. So, we're forced to look at maximum likelihood even though we're trying to do particle filtering. Okay, so it seems to me then, what I draw from this, what I conclude from this is that we just routinely will have to bundle some sort of maximum likelihood methodology in with particle filtering methodology if it's going to stand a chance of being, something that will come off, which will go off-road, right? I mean, particle filtering is great if you're driving down the road, but we want to go off-road, and as soon as we move out of dimensions less than or equal to 5, and as soon as we move away from toy linear examples, we're going to have to do this. Okay, so that's developing a general SMC methodology demands that. The other thing I would point out is that if you are going to use, you're trying to work in high dimensions, please don't use Gaussian errors. Because there's not only the problem I've just described about not being able to hit the ball, there's also an almost sure impoverishment feature going on there. You really should use something with a polynomial tail. Anyway, so as I'm sort of at this phase of winding up, why don't I wind up? So what's happened here, we've looked at the idea of trying to pick out a most likely path, a least action path, if you want to use the jargon of the physicists. And we find that we can do this if we look at the action, we do some calculus of variations, we end up with a second order differential equation to be solved with boundary conditions. If we expand around the least action path, we understand how the process looks around the maximum likelihood path. It's the maximum likelihood path plus some sort of Gaussian process perturbation. And in a sense, if you were trying to do some SMC, this would guide you in how to simulate your paths. I mean, you wouldn't, you'd have your basic maximum likelihood path. You generate some paths according to the law of the Gaussian perturbation around it, and these are paths which make sense in the context of that particular problem, rather than just kind of blasting out lots and lots of Gaussian paths and sort of Brownian paths and hoping that some of them are going to be close. They're not. Now for large T, there are issues here, because for large T, what are you trying to do? You've got this second order differential equation, you've got a boundary condition at time naught, you've got a boundary condition at time t, so you've got to basically do some sort of shooting method. So you start off with a particular value of x naught, you look at the condition at time naught, that tells you what the gradient has to be at time naught, you follow the solution along, maybe you got zero derivative with respect to p at time capital T, or maybe you didn't. If you didn't, you have to adjust so that you get zero derivative at time capital T. However, the longer t is, the more unstable, the more fiddly that numerical solution is likely to be, and you probably won't be able to identify the correct initial condition. So you can't make t too large. In that case, you've got to develop some kind of recursive methodology. So what I think we will do, and what I'm hoping that Valentin will be doing very shortly, is to try and understand how we could, say, solve up from time naught to time 1, and then we've solved, we know the conditional distribution at time 1/2, so we could then solve from time 1/2 to time 1.5. We know the conditional distribution at time 1, then we solve from time 1 to time 2. So we could kind of piece it together by sort of rolling chunks of the differential equation forward, using the solution from the previous chunk to tell us what prior distribution we should use to start off the next chunk. So I think that's a potentially feasible way, but it's clear that you can't just keep on making t bigger and bigger and hope this thing's going to work, because it just isn't. So you have to come up with some sort of recursive methodology. I think it offers some hope for high-dimensional problems, because we're relying on a methodology for solving ODEs in high dimensions, which is basically fairly well developed. But we do need a lot more work now on the theory and the examples. So that's all I have to say. Thank you.
Question? If you want.
There's work of Kusoka and Stroop that look at the asymptotic expansion of densities of diffusion processes. And so you mentioned, so this work that you have done, of course you can, if you ignore the bottom half of your vector, you are just telling us something about how the distribution of the signal, the prior distribution of the signal is. And you are saying the prior distribution of the signal is, in effect, some Gaussian centered around the path of minimizing action or something like that. But what they have a result which says that asymptotically, the distribution is not like that. It's not going to be Gaussian. And they use
Asymptotically in what sense?
Asymptotically in the sense of getting the time smaller and smaller.
Okay, that's not what I'm considering here.
Well, they should apply, I mean, the two should match for small times. I can show you the paper, but definitely they do not, they have a path, and this is the path sort of, is not, probably not your path. But, you know, what's around the path is definitely not a Gaussian. So there might be scope to
Okay, we should talk about that. But I think we're what you're describing sounds to me a priori like it is a different study from what I'm undertaking here.
Yeah. There's not something about the distribution.
Yeah.
I agree with you. For large T, of course, if you have optimization from 0 to T, after that, maybe another one starting from another original point. That happens in polymer type simulation where you have a random environment and you don't know where is the big place to go. So you find a very nice place, and a new one arrives, and this one tells you that it's better to be in bad place in the beginning and be in the best place after that.
Truly.
So in this so I agree that the recursive methodology is useful, but we still have this problem. Optimizing, maybe after some step, what we have done is not the best.
Sure. No, that's a very, very fair point. I mean, it's you might be thinking of some sort of system which was unlikely to say tunnel through to another well, say, and at some time it's going to have to happen. But if you're just going to take it in little pieces, it could never happen. Whereas if you look over the longer time scale, it can. Absolutely true. I mean, you make a very good point. I think any general methodology is going to be defeated by particular examples somewhere.
And the use of recursive would be related to some observability questions. To say,
I don't know. I mean, my hunch is that the way I'm planning to tackle this is just to say, we solve it out from time 0 to time t, and we choose an intermediate time. When we solve from time 0 to time t, we know the distribution, conditional distribution at that intermediate time. We'll treat that as the prior now for the next solution period. So you can forget about what happened before that time and just go ahead from there. So it seems like the first thing one could try to do. I mean, it may even be sufficient to go out from time 0 to time capital T. We now have, when we've solved the least action filtering problem, we now have the distribution, the conditional distribution at time t. So we could maybe even just go straight on from time t to time t plus 1, say. I don't know.
I have two questions. You said that near the
optimal trajectory axis behaves like Gaussian descendant. In which sense?
Ah, yes. It's a very good question. In which sense? Yeah, I mean, all I can say is that if you look at the log likelihood and you expand it in the unknown variables, which
And you have to let something go to zero.
Yeah, absolutely.
And what is this
Yeah,
something?
Yeah. No, you're absolutely right. Look. I mean, we're talking about asymptotic maximum likelihood theory, right? And you know, we have distinguished colleagues in statistics who do this sort of stuff properly, and then there are people who actually use this for real, right? Now, these distinguished colleagues in theoretical statistics, you know, have conditions, you know, A1 up to A16, none of which, of course, can be checked in any given example. But assuming A1 up to A16, then, you know, some statement about asymptotic distribution. Now, in practice, nobody could check or would check. So, you know, my attitude is that we should, you know, you're right, somebody has to take the trouble, and it probably isn't going to be me, but it should be made precise. But it's at the same, I would say it's at the same level of rigor and reliability as asymptotic maximum likelihood theory as it is used in statistics.
Okay, and the second question is, so you apply your, say, methodology to Kalman filter,
Yeah.
And you are interested in the behavior on 0-1, on the time interval 0-1. At point 1, you get your estimate. Does it coincide with conditional expectation?
The correct Kalman filter. I haven't checked that, but I'm pretty sure it will, because because you get. I think I'm right in saying that the I think you just end up with, as it were, a first order differential equation for the estimates. I think it is the same thing, but I should verify that. But that's a very good
Okay,
question.
if there are no more questions, then let's thank our speaker again.